Okay, so for part C it says, hence or otherwise find the set of values of C such that the graph of y equals f of x, that's this graph here, this is f of x, has a point of inflection with zero gradient, one local max and one local min, and no points where the gradient is equal to zero. Okay, so it says hence or otherwise. So the hence or otherwise, guys, refers to part B where we got this first derivative. So we're going to use this first derivative to answer this question, and we're going to use these graphs that I've brought into this video from the previous question. This was the graph when c equals -1. This was when c equals 0. These two were given to us, and these were the two we sketched. So before I show you how we know, or a more kind of technical way of figuring this out, let's see if we can just, because it's only 1 mark, 2 mark, and 2 marks and 1 mark. So you'd actually get the marks, certainly for these two, if you just write down the answer. Which of these has a point of inflection with 0 gradient? Well, it's this one, because, well, they all have a point of inflection. This is a point of inflection there. That's where it changes from concave down to concave up. This is a point of inflection there, concave down to concave up. This is a point of inflection there. In fact, they all have points of inflection. There's a point of inflection there. Here's a point of inflection there. They all have a point of inflection at 0, concave down to concave up. But which has a point of inflection with a 0 gradient? Well, that's this one. And you might even know just the graph y equals x cubed. It looks a bit like that, or it looks like that, but it's here. It has a point of inflection and a 0 gradient. You'll see right there, right on that point, the gradient is 0 just for that moment. Here, the gradient is not 0. It's still a positive gradient. It doesn't become a stationary point. That's that special point of inflection that also has a stationary point. Okay, so the answer to part 1 is actually 0. I'll show you again a more technical way to do that. Part 2, 1 local max and 1 local min point. Well, which of these graphs have 1 local max and 1 local min? Well, it's these ones. And this is for c equals 1 and c equals 2. And I bet you if you do c equals 3, c equals 4, c equals 100, c equals 1.23456, you would also get 1 max and 1 min. So the set of values of c are, it has to be greater than 0. And then similarly, at no points where the gradient is equal to 0, that's this one. There's no turning points, no point of inflection. Is this one. It's for the negative c's. Now that's just from kind of observing the graphs, but let me show you the more technical way to do it. So I've brought in f of x and f dash of x that we got from part B. When I see point of inflection, straight away I think second derivative. So let's get that second derivative. The second derivative is equal to 6x, because this is a constant. So it's just 2 times 3 is 6x. Now, point of inflection, it's where the second derivative equals 0. So I'll write that down at POI, that's point of inflection, f dash dash of x equals 0. Therefore 6x equals 0, therefore x equals 0. So we know the point of inflection is at 0. Got it. And you can see that's true for any of these because there is no c. It's independent of c. So it's always going to be at 0. Then at 0, if I sub in here, f dash of 0, if I sub in 0 into this, I get 3 times 0 squared minus 3c is equal to 3c. Now, if this has a 0 gradient, then if gradient is 0 at x equals 0, then f dash of 0 has to equal 0. So special case, if it has a point of inflection and that also has a gradient 0, then the first derivative equals 0 and the second derivative equals 0. So the first derivative has to equal 0, hence 3c is equal to 0, hence c is equal to 0. Now you may say, hang on, 1 mark to do all that work? Well, you can nearly almost do it in your head if you understand what I'm doing, and if you can kind of see it from the graph, you can write down the answer. But certainly I wanted to show you why it makes sense technically. But you would get the answer for writing c equals 0, or you get the mark, sorry. Part 2. 1 local max and 1 local min. Right, if it has 1 local max and 1 local min, that means the first derivative has to equal 0, and there should be two solutions. So I need 3x squared minus 3c equals 0. If it has a 1 local max, 1 local min, that means it has 2 stationary points. So I should have 2 solutions here. So I have 3x squared equals 3c. 3's cancel. X squared equals c. So x is equal to plus or minus the square root of c. How can this have 2 real solutions? Well, c has to be positive, because if it was negative, we can't get the square root of a negative number, not to get a real solution. So c, therefore c has to be bigger than 0. That will give us our 2 stationary points, hence 1 max and 1 min. And then finally, you probably can see where this is going now, because I've done this. Same thing, no points where the gradient is 0. Well, if the gradient is 0, then again, this equals 0, this equals this, x squared equals c. How can this situation have no solutions? Well, if c is less than 0, because it's the exact same equation, but if c is negative, for example, imagine c was negative 9, then you've x squared equals negative 9, there's no real solution, so you can't do it. Okay, so that's it, guys. Part C. For part I, a point of inflection with 0 gradient is this situation, so c is 0. 1 max and 1 min is this situation, c is bigger than 0, and no points where the gradient is equal to 0, that's this situation, and that is for c is less than 0. Okay, that's it, guys. Hope that makes sense. Part D in the next video.